Welcome back to our discussion, How to Benefit from Model-Based Systems Engineering, sponsored by Noblis here on Federal News Network. My guest today is Pat Maharg. He's the Chief Architect for Model-Based Systems Engineering at Noblis. I'm your moderator, Tom Temin. And we were talking about interfaces earlier, and I wanted to talk about the human interface to the digital twin, to the system that is our model-based engineering effort here. In CAD, there is a drawing that you can see and manipulate. In digital twins, what is it? Is it something you see physically, or in the case of software, you just have a list of lines of code?
So today we use model-based system engineering tools, and there's quite a few vendors out there, and it's a visualization tool. Underlying the visualization tool, we're actually in there drawing diagrams. And those diagrams are based on what we call the SysML language. And the SysML language helps us define and describe the relationships between those diagrams. And you can think of it as a schematic. So a schematic has a lot of icons and symbology on it. Model-based system engineering uses the same approach. So when we look at the diagrams, everyone understands what those icons look like or what those schematics look like when we go to consume them and capture them. So it's a software tool. We run it on our desktops. Usually we use pretty large monitors because sometimes our diagrams can be very big.
Right. So then the implication is that there's something to learn here. That if you are an engineer used to the traditional tools, we used to say, you have to give up the slide rule and go to CAD. Now you've got to kind of leave CAD behind and go to this SysML language and so forth. Tell us more about the human requirement here.
So folks that are interested in model-based system engineering, there's quite a few ways that you can learn. So universities now are starting to teach SysML, and I'll call it SysML 101, 102, or the language and the tool usage at an undergraduate level. Probably 5 years ago, that was normally taught at a graduate level or a master's degree. So usually it takes folks, in my opinion, a year or more to really get to understand model-based system engineering. And it's really, we're not reinventing system engineering at all. We're still using the same rigor that we're all used to, but we're just capturing in a visualization tool. So yeah, to make that transformation, a lot of people are very interested in digital engineering transformation, and you'll hear those terms as well. And model-based system engineering is part of that transformation and training. So inside of Noblis, we have our own training pipeline, and we teach those classes. And it's a lot of modeling, it's a lot of practice, and it's a lot of helping, guiding, over the shoulder, teaching people how to actually where to click, how to create those things in the model.
And who should be having some expertise in this? Clearly design engineers and systems planners, but because of the interfaces that have to do with life cycle costing and whatever other parameters you need to know about in the future, for example, what wear out cycles might be, replacement cycles, it seems like there should be interfaces to the maybe acquisition and financial people, and also the logistics people in the case of a military system. So who needs to know this, and who simply needs to be able to look at it and understand what it's telling them?
So that's a really great question. So model-based system engineering is hardcore engineering at its essence. But from a approach perspective, what I teach an engineer, a system engineer, on how to model and how to build those diagrams is very different from acquisition perspective of a program manager or a project manager or a senior decision maker. They really don't need the nitty-gritty details down and in. So using the tool correctly, we can bring those details up in abstraction and do analysis to answer the what if question. So when we build these very complex models, we build them not knowing what the question is going to be, but having the data available to do the analysis to say, well, what if I do this? What if I do that? So from a senior leader perspective, model-based system engineering tools are very detailed. There's a lot of the SysML language you have to understand. So it's difficult sometimes for them to consume it, but it's on the system engineers to draw or build that diagram at the level of abstraction needed for that decision maker.
Right. And you said it's about a year, basically, at a minimum of intensive training to be able to become proficient in this.
I think so. And it's, you have to practice quite a bit. So there's a lot of information to learn. It is a language. So you have to understand the symbology of the language first. So that's always, in my mind, step one. And then as you go, and it's definitely a team sport. And what I mean by that is model-based system engineering is always done better, in my opinion, by 2 or 3 engineers, because we peer review each other's work. And we're always looking at these diagrams and saying, well, this is what I see. Is that what you intended? So, so that's usually how we work in teams. Sometimes those are large teams. So yeah, and it's a lot of mentorship, I would say. It's a lot of guidance.
And just as an aside, does this system of development work also for infrastructure, like bridges and structures and buildings and so forth?
Absolutely. So system engineers are pretty jack of all trades, master of none. We're very universal, and we think of things from a systems perspective. So when we do analysis of we're going to build a new model, from us, in my mind, it's not much different thinking about an aircraft carrier as opposed to a building. It has parts and it has the interfaces. There's requirements or standards that it has to meet. And the structure of how we put it together, same thought process. But we're always looking at the big picture. And then we get these other disciplines as subject matter experts to help us. So in the case of a building, we need a plumber. So that plumber has to come in and make sure that we're doing in accordance with code, or an electrician.
Right. And so what then is the unique selling proposition of model-based systems engineering to traditional engineers who are quite happy with the tools they have now?
That's a great question. So the return on investment, I believe, is we can build a better system and have better understanding earlier in the process. So if we understand what we're trying to build from a stakeholder perspective, and we do it in a digital environment, I can change it very quickly. And so I can increase the time, or actually decrease the time for delivery of developing that system. And if we decrease the time, we're going to, of course, hopefully decrease cost as well. The other thing that I believe is very important on the return on investment is we can start to verify and validate that digital twin before we build something. So in the past, classic system engineering, we would go engineer, then we would go build and test. Now we can really decrease that time, getting to verification and validation, to think that, yep, I think we have it right, or right enough to go build.
And earlier you mentioned something I want to follow up on, and that is that the digital twin, or the engineering artifact, let's say, goes with the finished product through its life cycle. What does that mean in different contexts?
So an example of that would be if we created, and I'll use a ship as an example. So ships, like we mentioned, have very long life cycles, 30, 40 years. Over that life cycle, every 2 to 3 years, we're either refreshing or updating something on the ship. So, and ships have large shipyard periods. So what we can do is take the model that's already built, do an analysis on the piece that we're going to go in and replace, only create that part of the model, update it, and plug it back into the larger model that's going across the life cycle. As opposed to in the past, system engineering, we would build something 2 or 3 years later, we would start basically again with a clean sheet of paper and say, okay, now we got to go do this update. And we didn't have a lot of the information. We'd have to go find it, or get it off the shelf somewhere, and then recreate it over and over and over again.
Does model-based also help you avoid some of the common mistakes that happen even in the most sophisticated design systems and well-intentioned people? Sometimes, in a ship, again, to continue with that example, someone will have the idea of a cable going from point A to point B, but somehow along the line, a bulkhead there didn't get seen. So next thing you know, you're, acetylene torch cutting a hole in a bulkhead, retrofitting the ability of that wire to go through from point A to point B.
That's correct. So once again, that's a good example of interfaces. So when we start to think about the interfaces, we can quickly add or subtract or change that interface in that digital twin. And through peer review and taking our design in that model and showing it across the different disciplines, now we're making sure everyone gets a chance to review that in a digital format. But like you said, when I go to glue part A and part B together and think that they're going to fit, and come to find out two different disciplines built it, it doesn't go, square peg, round hole. Now what do we do? So I truly believe that we can catch those problems earlier. And we also, the other part of that is we can do a better job of planning future capability. And what I mean by that is, from, once again, an interface perspective, if we know that some type of new sensor is going to come to that platform, but we know it's not going to get here because it's brand new and the technology isn't mature enough, we can already build the stubs of those interfaces in the digital twin and plan for that, instead of having to go back and now, for instance, have to rebuild a whole wiring harness. We could go ahead and put those wires in that harness, knowing full well in 18 months, we're going to plug something new in.
And what about the idea of maintenance and repair and operations? I mean, any kind of military platform, for every hour it might be in deployment, it's at least an hour in maintenance and repair. And so that's the big life cycle cost tail, as you mentioned earlier, to these systems. But very often, you see this even in the consumer world. Items that are complex are designed for and by the assembler without maybe enough forethought for the person who's going to have to fix this thing later down the line or maintain it. Can a good model-based design approach help you design for the future maintainability, and therefore maybe enhance military readiness by shortening the maintenance and cycle and cost?
Yep. So that's a great example. Model-based system engineering, we're thinking of that from a requirements perspective. And at a higher level of digital engineering, now virtual twins in the virtual environment are being used and built, especially by maintainers. So from a system engineering perspective, we make sure we have the requirements covered in the structure of the system built. The next step of that is they can use our metadata from our model and start to create these very complex virtual reality simulations based on the true engineering coming out of our system model that helps create that. And then they can do that maintenance in that virtual world to make sure that they can get to the nuts and bolts. Or do I have to take off 5 pieces in order to get to this one piece? Can we redesign it some way? So that's what the digital enterprise is now starting to do, is glue together the hardcore requirements all the way through the system and then to that maintenance. So that's a great example.
And very briefly, can this maybe speed up the time spent in design and development, but shorten the time spent in field testing, because you come closer with your prototype to the final requirement, maybe with the model base, than you would have by traditional means?
Yeah, I believe so. And over time, once we build these complex models and we verify them in the digital, and then we take them to the physical and validate it and say, yep, we got it right. Now we can reuse parts of the model that we built on other systems. So now we're taking it, I call it the Legos. We can take the Legos apart, snap them together a different way. And we've shortened the verification and validation because we've seen that it does work. So we can really get down to the nitty-gritty of what interfaces we need to test or what functionality from a test perspective, because we have high confidence that it is in fact going to work.
So you've built yourself a knowledge management platform in some ways.
We have, yes.
All right. Interesting discussion. I want to thank our guest today is Pat Maharg. He is the chief architect for model-based systems engineering at Noblis. I'm Tom Temin. You're listening to Federal News Network. For more information, please visit federalnewsnetwork.com and search Noblis.